Okay, I've had a couple of people request that I do a video on dilution math. Disclaimer, I put this together in like half an hour. So it's not going to be as like in depth as my other stuff that I've walked you guys through. It is, however, I'm hoping going to help a little bit with understanding what the heck is going on. We're going to start with like pulling it back and doing like the general math overview, and then we'll push in and really like dig into like what it is to do dilutional math, okay? There are a bunch of reasons why we do dilutions. You can look through this. It's not super important, but just know that there is a ton of applications for dilutions in the clinical laboratory. And so this is a fundamental foundational skill that you really do need to figure out how to do. So, real quick, bunch of definitions. What is a dilution? A dilution is reducing the concentration of a solution. We are adding something to a concentrated solution to make that concentrated solution less concentrated. We can do that by adding a solvent or a diluent. That is the thing that we use to dilute stuff. We are diluting our solute. So the thing that we're trying to get to be less concentrated is our solute. Usually in the clinical laboratory, your solute is going to be your patient specimen. They're going to try to trick you by saying that you have added your patient specimen to another thing. The patient specimen is the thing that we are measuring for at the end of this. It contains the thing that we are trying to analyze. So we are always going to be treating the thing that we are trying to analyze as the solute. So just because they say that you are adding your patient specimen into a solution, it doesn't mean that that is suddenly the solvent. It just means that it is the thing that you are trying to analyze. So treat the thing that we are trying to analyze as the solute, even if you are adding the patient specimen to something else, if that makes sense. If not, ignore it. Now, let's get into the math real quick to talk about it real quick. Dilution ratio is comparing the amount of solute to the amount of solvent. You are comparing one part to another part. Dilution is comparing the solute to the total volume. So you are comparing one part to your whole. Dilution factor is how we represent the relationship between your concentration of, how do I want to say this? Dilution factor is the way that we can take the concentration of either the original solution and use that to find the concentration of our final solution, or we use the endpoint solution's concentration to find the concentration of the original specimen. We'll get into that in a little bit. Don't get hung up on the details right now. I promise we'll get there, okay? So, what the heck is a ratio? Let's start with something we can see. Let's start with something that's not super theoretical. Let's start with something, dare I say, easy. So, I have put a bunch of fruit on this slide, okay? There are 12 apples and 8 oranges. There are 20 total fruits. Now, I can compare apples to oranges. I can also compare apples to my total, and I can compare oranges to my total. If I compare my apples to my oranges, I have 12 apples per 8 oranges. We can simplify that down into 6 to 4 because I'm just dividing each side by 2. And I can simplify that further into 3 to 2 by, again, dividing by 2. This implies that for every 3 apples, I have 2 oranges. Okay? Again, I can also do a comparison of my apples to my total fruits. So I can do 12 apples to 20 total fruits. If I am comparing a part to a part, I will use a colon. And you can remember that because part to part, I have 2 parts. I'm comparing 2 things. Okay? If I'm comparing a part to my whole, I will use a fraction. Does that make sense? You can remember it because there is one line and there are 2 dots. There is one part and there are 2 parts. Cool? Cool. We can simplify this fraction down into, I'm just going to divide both by 2, 6 over 10, which then breaks down into, again, dividing by 2, 3 over 5. This fraction here implies that for every 5 fruits that I encounter, 3 of those fruits will probably be apples. Does that make sense? Do you notice like the change in verbiage there? So for the first one, what I was saying is that for every 3 apples that I will have 2 oranges. The second one is saying that for every 5 fruits that I pick up, 3 of them will be apples. It's a little bit of a different way of looking at the relationships that are going on. I can do the same thing for oranges. I can do 8 oranges over 20 total fruits, and that breaks down to 4 over 10, which then breaks down to 2 over 5. Kind of like the previous fraction, this is saying that for every 5 fruits that I pick up, 2 of them will be oranges. Cool? What if we can't see the difference, right? On the previous example, you can physically see that there is a difference going on. I don't really care particularly if I'm picking up an apple or an orange. It's not my problem. Just apple, orange, I'm happy with either. But what if there is a difference and I need to know very badly about one of them? So let's say, for example, you are like my friend who went to a Halloween party last year and went bobbing for apples. My friend happens to be allergic to only green apples. I don't know why. I don't know what the mechanism there is, but he is allergic to only green apples. This man made the decision for some ungodly reason to get blindfolded and go bobbing for apples in a barrel of apples that contained both red and green apples. He did bite into a green apple. He did have an allergic reaction. But let's talk about the math here to explore this as an option, okay? So again, I have 12 red apples, I have I have 8 green apples, and I have 20 total fruits. So I can compare the red apples to green apples, I can compare the green apples to total fruits, and I can compare the red apples to total fruits. But the thing is, my friend is only allergic to green apples, so I don't really care about the chances of him biting into a red apple. I only really care about the relationships that involve green apples. So I really only care about green apples to red apples and green apples to total fruits, right? So green apples to red apples, it's going to be 8 to 12, which breaks down to 4 to 6, which breaks down to 2 to 3. So for every 2 green apples he encounters, he will encounter 3 red apples, is what this is saying. For every, For 8 green apples in the system to 20 total fruits, breaks down to 4 over 10, breaks down to 2 over 5. My friend has a 2 in 5 chance of biting a green apple if he goes bobbing for apples blindfolded in this barrel, which means he has a 2 in 5 chance of having an allergic reaction. This is why we care about this kind of thing, is because it tells us the concentration of green apples that are present within this distribution. How many green apples are present compared to red apples, and how many green apples are present compared to the total number of apples that are here. It gives us an ability to figure out the chances of him encountering something that might make him feel not so great. Why is my phone ringing? Sorry, some council stuff. Ignore that. Anyways, the thing is, we can apply this to the laboratory, quite literally. You may not be able to see it with your eyeballs, but the same principles will still apply. We have a test tube, we mix stuff together, we have a reaction occurring, we have a different distribution of things. We can still do these same ratios, right? We can still compare 6 blue molecules and 4 red molecules. We can still compare how many red molecules we have to the total number, and we can still compare the number of blue molecules we have to the total, right? So I can still do 4 to 6, which breaks down to 2 to 3. I can still do 6 blue molecules over 10 total molecules, which then breaks down to 3 over 5. I can still do 4 red molecules over 10 total molecules, which then breaks down to 2 over 5. I can still do these same setups. I can still do my ratio. I can still do my comparisons of individuals to the total. just because it's suddenly chemicals, it doesn't change the principle of what is occurring. So now that we understand that, let's do some math, okay? So let's do the same thing in a tube. I have a patient specimen. My patient specimen is 1 milliliter. Okay, lovely. Now I add in some diluent. Let's say I add in 1 milliliter of diluent. Okay, I have 1 milliliter of patient volume. So I have patient, I have 1 mil. A diluent or solvent, however you want to refer to it, I have 1 mil. I need to do my total volume that is present in the tube. I would add these two things together. So that is 1 plus 1 is 2 milliliters. Total volume, 1 plus 1, 2 milliliters. Okay? I can compare these two things. I can compare these two things. And I can compare these two things. So I can do patient to diluent, so 1 to 1, because this is my patient, this is my diluent, 1-to-1 ratio. And then I can do my patient to my total, right? I don't really care so much about the diluent. It's not my problem, right? I'm not trying to measure what's in my diluent. I'm trying to measure what's in my patient. I'm trying to measure my green apples. I'm not trying to measure my red apples because I'm not allergic to my red apples, right? So I can see that this is a 1-to-2 dilution, and it is a 1-to-1 ratio. I have a 1-to-1 ratio of patient to diluent. I have a 1-in-2 dilution of patient to total volume. Does that make sense? Okay, let's change the numbers up a little bit. So let's say that I have my patient volume. Let's say I have 50 microliters, and I add, let's say, 100 microliters, right? So I have patient is 50 microliters, and my diluent is 100. Should probably try to make sure I can write 100 microliters. To find my total, I just add those together. 150 microliters is my total volume. 150 microliters is my total volume. Okay, so I have 150 microliters in total. I can do my comparison of patient to diluent, so 50 to 100, which would then break down, divide both sides by 50, you would end up with a ratio of 1-to-2, right? I can also do my patient 50 to my total volume, 150, divide by 50, and you would end up with 1/3. Does that make sense? Because I just divided that by 50, and I divided that by 50. 150 divided by 50 is 3. 50 divided by 50 is 1. That's how I got 1/3. Okay? Beautiful. That's it. That is how you would get your ratio and how you would get your dilution. Ugh, isn't that beautiful? Problem is we haven't talked about factors yet. So what is a factor? Well, in this context, right, let's say that what we just did, right, we have 50 microliters and 100 microliters. So let's say I have 50 microliters and I have 100 microliters. But let's say that this patient specimen, now we'll get to that in a second, I'll add that at the end. My total volume is 150 microliters, right? Because I added 100 plus 50, which means that my ratio between these two things was, again, 50 to 100, which breaks down to 1-to-2. My dilution is 50 over 150, which again breaks down to 1/3. Okay? Beautiful. What the heck is a factor? Well, let's say that I took this 1/3 dilution and I put this 1/3 dilution on the analyzer. And the analyzer analyzes it, spits it out, and tells me, hey, your albumin that we just measured is, doing the math in my head backwards real quick, is 1.8, I think it's either grams or milligrams. I think it's grams, whatever. Your analyte is 1.8 grams per deciliter. Do we think that 1.8 grams per deciliter is reflective of what was actually in the patient specimen? No, right? Because this is our original patient specimen. This is what we just stuck on the analyzer. We just made that concentration of the patient specimen go way down. Well, we're over here trying to measure the concentration of something, but this concentration is not reflective of what it is that is in the actual patient sample because we messed with it. We screwed it up. We made it weird. We don't want to try and take that and apply it and report 1.8 grams per deciliter out to the physician because it's not reflective of the actual patient state. And what happens if you tell the doctor something about a patient? What happens if you report out patient results? Well, the doctor is going to treat the patient for the results that you give them. In some instances, the doctor can kill the patient if you tell them something wrong. So it's really important, especially when we start getting into values that can be critical, like potassium or anything like that, to not mess this up, because the doctor is going to administer something to fix that problem, and it might kill the patient, and that's a problem. So how do we get back to the amount that we originally had, right? Well, all that we have to do is multiply 1.8 times 3. Why 3? Because we diluted it 3 times. That is why we use this for math and this for ingredients, for building, for stuff like that. The ratio is useful for instructions and SOPs and guidance manuals. It's not as useful for math. It is useful for math, but it's more useful for building. You can think of the ratio as a cookbook, right? If you open up a cookbook, it'll tell you to use 1 egg for every 3 cups of that's a horrible ratio. Please don't use 1 egg for every 3 cups of vegetable oil. But that's my point, is that's a ratio. You use a ratio of 1 egg to every 3 cups of vegetable oil versus 1 egg per cake would be closer to this, right? This is more useful for figuring out the concentration of how much egg is within your cake, or how much of the volume of, you get what I'm trying to say. Anyways, this is helpful for math. So you would multiply 1.8 times 3, which ends up working out to, what is that? 54? Is that 54? I haven't done old school math in a long time. Clear, 1.8 times 3. Yeah, 5.4. Cool. Yay. Okay, so that would give you that your original concentration was 5.4 grams per deciliter. Now, why does that work? We put our specimen, we originally had 50 microliters. I should try to write genuinely, right? I added 100 microliters into that. I now have 150 microliters in total. I have the ability, the total volume of this solution is 150 microliters, which is 3 times the volume of the original specimen. Does that make sense? That's why we worry about this. The new volume is 3 times the volume of the original specimen, which means we have messed with our concentration by a factor of 3. So we have to undo it with a factor of 3. That is why it is called a dilution factor. It's into math. Math factors are a multiplicative thing. So it's a number that you multiply something by. That's a factor, right? We use 3 in this instance because our original volume to our total volume. Our total volume is 3 times the original volume of our patient specimen. Does that make sense? Okay, we're going to do something a little bit ugly. I'm so sorry, but we need to explain one more thing before you are finally prepared to fully understand what's going on, okay? So let's say I have my patient specimen. And let me do something in my head real quick. Okay, so let's say I have 3 milliliters of patient specimen, and I have added 5 milliliters of diluent. So my total volume is 8 milliliters, okay? My ratio is 3 to 5, because it's patient to diluent. My dilution, though, is going to be 3/8. Ruh-roh, I can't simplify that down, right? That's ugly. I don't like that. What do I do? Because now I don't really like fully know math-wise what I'm supposed to do. Well, there are 2 mathematical options, and I'm going to give you the easiest one, okay? I don't want to do a bunch of math explanations for you, so I'm going to give you the easiest way of doing it that keeps this as simple as possible and keeps you on track for dilution factors. So if what we just talked about a second ago is that your dilution factor is just your denominator, the only reason that it can be just your denominator is if your numerator equals 1. So we need to mess with this fraction to make your numerator equal 1. How do we do that? We divide both your numerator and your denominator by 3. You are allowed to do this. I promise you it will not make a difference in your math. So you would divide 3 by 3 and you would divide 8 by 3. 3 divided by 3 equals 1. 8 divided by 3 equals 2.67. So your new ratio is 1/2.67. You can either, when you do your dilution, you can report it as 3/8 or 1/2.67. Different professors will prefer different things. You will need to ask each of your professors what they prefer. Personally, for me, I prefer this one, just because you can then come right down here and say that your dilution factor is 2.67, and you don't have to worry about being like, it's 3/8 or this. You can get away usually with this specific version, but technically speaking, this is also correct, if that makes sense. Like it doesn't necessarily matter. Different professors have different preferences. Check with your professor to see which version that they want. The math is the same either way. So let's say that I put this 1/2.67 dilution on the analyzer, and the analyzer comes back and tells me, hey man, we just did our stuff and it came back that your patient specimen was 25 nanograms per milliliter. Are we going to report out 25 nanograms per milliliter to our patient? No, because that's not what's reflective of the actual sample. That is, they're diluted. Well, we need to work backwards to get our original sample. We would just multiply it by our dilution factor. So it would be 25 times 2.67, which is 25 times 2.67, 66.75. 66.75 nanograms per milliliter of patient specimen. This would be the reportable value that you would push out, because this is the value that's reflective of what's actually going on in the patient's body. Cool? Awesome. Let's practice. So I have 0.75 milliliters of patient sample that is required to make a 1/4 dilution. So I have 0.75 milliliters, and I am diluting 1/4. So my patient sample equals 0.75 milliliters, and I am required to make a 1/4 dilution. Okay, what is the total volume? How much buffer is required? What is the dilution factor? And what is the dilution ratio? Well, first and foremost, the easiest question to answer is, what is the dilution factor? Well, our numerator is already 1. Phenomenal. Don't have to do any extra math. So our dilution factor is just 4. All right? Now, another nice thing, when your numerator is 1 and your bottom denominator is a whole number, your dilution ratio is literally just going to be 1 to your denominator minus your numerator, which is 1. So in this instance, it's just going to be a 1 to 3 ratio. Okay? So we have 4 total parts. We have 4 total volume. One of those parts is our patient specimen, and 3 of those parts is our diluent. Sorry, I don't know why I just fully blue screened there. Anyways, so our dilution factor, another way, if you're a visual person, you can take your patient specimen, you can divide it up into the number of parts in your dilution factor. So our dilution factor is 4, so I can take my patient specimen and I have 4 parts of, or I can take my like final volume patient specimen and divide it into 4 parts, right? So I have 4 parts here. Because I have a 1 to 3 ratio, one of these is going to be patient and 3 of these are going to be diluent. Okay? The reason I'm saying that and harping on this idea of like parts versus like total volume versus like relationship between that is because we know that the patient is equal to like 1 part, right? Patient equals 1 part. And we also know that the patient equals 0.75 milliliters, okay? Well, we know that our diluent is equal to 3 parts, which means that if we know the value of 1 part, we can just multiply the 1 part by 3, and that'll give us our 3 parts. So if 1 part equals 0.75, we would multiply 0.75 times 3. 0.75 times 3 is, what would that be? 1.5, 2.25, right? I think it's 2.25. Yeah, it's 2.25. Okay. 2.25 mils. Okay. So our diluent, our patient sample is our solute. Your buffer is going to be your diluent. We have just solved for that, so that's going to be 2.25 milliliters. So then we can come over here, 2.25, 2.25 plus 0.75, 3.0 milliliters. Does that make sense? I know that we went kind of backwards. It's because that's how I think about this. I think about it very backwards compared to everybody else. We suffer through it. Okay, let's do another one. I have 0.38 milliliters of patient specimen. So 0.38 milliliters. Patient specimen. How much how much buffer would be required to make 0.38 milliliters of patient sample is required to make a 1 in 7 dilution. Well, we can also work backwards from here. 1 in 7, because this is a 1, we can literally just rebuild our fraction the same way that we rebuilt the ratio up by doing that fancy thing that I showed y'all. Where is it? Right here. We can do the exact same thing in the opposite direction. This only works because this is a 1. Heads up. So if this is not a 1, you have to do that math that we did to get them both to be, or to get this number to be 1, if that makes sense. So we can now do our second number, I guess, plus 1. So in this case, that would be 1 over 7 plus 1 equals 1 over 8. My key is wrong. Oh, it's because I didn't put in the answers for this one. We're going on the fly. It's okay. So that is going to be our dilution, 1 over 8. Again, we can just grab our dilution factor from this because this is 1, right? Which means that our dilution factor is just our denominator, so it's just an 8, okay? So we know now that in our tube, we have 8 total parts. So 1, 2, 3, 4, oh no, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Wow, those are terribly distributed, but that is 8 parts within this whole sample, okay? So we have 8 parts in total because our dilution factor is 8. 1 plus 7 equals 8. That's where we got the 8 from. One of those parts is our patient specimen. 1 patient. 7 of those parts is our diluent. 7 diluent or buffer. What is the total volume? What is the volume of buffer? That's how we get there, right? So again, 1 patient part. We already know that that patient's 1 part is equal to 0.38 mils equals 1 part. We have 7 parts diluent. So because we have 7 parts diluent, we can just take our value for 1 part here, which is 0.38, and multiply that by 7, which equals 38 times 7, 2.66 milliliters of buffer. I swear I need to double check if I actually put this in my... There we go. I don't know what y'all just saw on my personal stuff. I will have to check this before I post it because I need to make sure that I didn't just expose myself for looking at like knitting patterns. Anyways, okay, which is the one I'm looking at? 0.38, 0.38, 0.38. There it is. Okay. One of my calculators is wrong. It's fine. One of these, I would be willing to bet that it's my computer is wrong, but that's fine. 2.66 plus 0.38. Okay, yeah, it's definitely my computer was wrong. This is roughly going to equal, to get the total volume, we would add our volume, so 2.66. We're going to round this to, we're going to add these together to get our total volume, which is going to be roughly 3.04 milliliters. My thing that generated this was like saying that this is going to equal 3. That's why I was like taking a second to be like, it's not right, but it's fine. It's off by like just the teeniest amount. So the total volume would be 3.04 milliliters. The buffer amount required would be our diluent amount required, so 2.66 milliliters. Cool? Sorry, I know that got a little bit hectic for just a second there, but we're okay. We're good. All right, let's do another one. 8 microliters of patient sample is diluted to 400 microliters. So we know how much patient we have. We have 8 microliters. And we know how much total volume we have, which is 400 microliters. From this, we can very quickly do 400 minus 8 to get the amount of buffer that we added, which is going to be 392. I need to get that out of the way. Yep, there we go. 392 microliters. So then we can compare, we can get our dilution by comparing our patient volume to our total volume. So 8 over 400, which then divides down to, what is that, a 1 in 50? Yeah. So that'll become a 1 in 50 dilution. And oh, beautiful, look at that. It's a 1. So we can just pop that down there. 50. Beautiful, right? We love that. It's beautiful. What is the dilution ratio? Well, again, this is 1. So all that we have to do is 1 to 50 minus 1, which is 1 to 49. So that is 1 to 49. How much buffer is required? Well, we already found that. It's 392 microliters. It's that easy. It's much easier when you have both volumes because you can just do all of the other math. It's a little bit more annoying when you have like, you start off with like your ratios or you start off with your dilutions and then you have to back build from there. It's easier when you start with your volumes. Anyways, let's keep going. No. It's too early in the slide to be making mistakes like that. 888.75 microliters of buffer is required to make a 1 to 79 dilution. So again, we have our ratio. So ratio is 1 to 79. Look at that, that's a 1. Cool. So that means that our dilution is going to be 1 over 79 plus 1, which equals 1 over 80. So our dilution is 1 over 80. Oh my gosh, it's also a 1. Yay! Our dilution vector is 80. Isn't that lovely? What's the total volume and how much patient sample is required? Well, I have 888.75, and I need to know how much patient I have, and I need to know how much total volume that I have. I am not going to draw 80 little parts within a tube. All that we need to remember is that we have 1 part patient, and we have 79 parts diluent. We know that 79 parts equals 888.75 microliters. We need to figure out how much volume is present per part. So to do that, you would say, I have 888.75 microliters per 79 parts. So then you would divide 888.75 divided by 79 is going to give you 11.25 microliters per part, which means, oh my gosh, it's per 1 part. 1 part patient, wow, I just need 11.25 microliters times the number of parts, which is 1, which is going to be 11.25 microliters. Wow, 11.25 microliters for my patient sample. Then I can add 888.75 plus 11.25 to get my total volume, which is going to be 900 microliters. So how much patient sample is required? 11.25 microliters. What is the total volume? 900 microliters. Lovely. Okay, we're going to do another one. What was I doing here? What's the final concentration? Okay, cool. So a 25 nanogram milliliter solution is used in a 1/5 dilution. What's the final concentration? Okay, so we don't have parts here. We don't have parts here. We don't have the volumes that we're working with here. We only have a concentration and our dilution. So what do? Well, what are we looking for first? We're looking for our final concentration with our starting concentration. So we started with 25 nanograms per milliliter, and we put it in a 1/5 dilution, which means that our result is going to be 25 nanograms per mil divided by 5, because we're just multiplying it by the fraction, right? So 25 times 1 divided by 5. We don't worry about that because 1 doesn't matter. 25 divided by 5, you are going to have a 5 nanogram per milliliter concentration as your final concentration. Does that make sense? That's why this is useful. Okay, let's get into something a little bit more complicated. This was a lot more straightforward. Let's do something complicated. You perform a 1/10 dilution, so 1/10 dilution on a patient specimen, and run a test on the diluted specimen. if the analyzer reports that the analyte you're looking for in the patient's serum has a concentration of 35 milligrams per deciliter, what is the concentration you should report to the patient? Well, we have tested our diluted specimen, our specimen that's been diluted by a factor of 10, and it said that we have 35 milligrams per deciliter. 35 milligrams per deciliter. On the previous slide, we diluted it by a factor of 5, right? We made it less concentrated. We made the value that is present within that specimen like less physically, like we just made it less available. So we divided it. Here, we're doing the opposite. We divided it. We need to get back to the original concentration. I've got a tube that originally had one of these parts that was just pure patient. And then I added in, 10 more or 9 more parts for a total of 10 parts. I'm not going to do all of them. Which means that this little bit got divided out by 10. How do I reverse that? Well, if one direction would be dividing, the opposite of dividing is multiplying, right? So 35, in this case, our dilution factor is a factor of 10. So we're going to do 35 times 10. 35 times 10 is 350. So the value that you should report out, the value of your original concentration, is 350. I also realized that I just said multiplying versus dividing here. I know that we multiplied by a fraction, but that's because multiplying by a fraction is the same as dividing, right? Because here we had a tube with specimen in it, and then we added 4 parts of diluent to make it like a whole thing. And then all of that got divided out here. And in dividing it out, we made it less concentrated. That's why we're dividing or multiplying by a fraction. Here, we've made it less concentrated, but now we need to report out the original concentration. So we have divided it. We need to multiply it back to get it where we need it to be. Okay? So last thing we're going to talk about is serial dilutions. I'm not going to go too hard on these. I just want you to physically know, like, kind of how to get there. Because I just need you guys to be able to look at it and be like, here's the formula. Here's how to solve it. Okay? So, serial dilution. A serial dilution is going to involve putting a specific amount into a tube, into a tube, into a tube, into a tube. So I take something and I put it into the first tube. Okay? And that is my pure specimen. And then say I have 9, what do I want to do? How do I want to make this easy on myself? Because I don't want to do math in my head. Let's say I add 1 milliliter of diluent to each of my tubes. 1 milliliter, 1 milliliter, 1 milliliter. And so I start here. This is my pure tube. Okay? I've added stuff into my pure tube. This is pure. I'm not counting this as my tube 1. I'm just counting this as the thing that is storing whatever is there. Okay? This is my tube 1. This is my tube 2. This is my tube 3. This is my tube 4. This is my tube 5. Keep in mind, sometimes this will be your tube 1. Read your question carefully and see if this is trying to tell you that this is your tube 1. I'm just being lazy right now. This is not my tube 1. This is just pure sample. Let's say that from my pure sample, I take 1 milliliter and I put 1 milliliter into here. And then I mix this 1 milliliter with this 1 milliliter. Well, I now have 1 milliliter of specimen to 1 milliliter of diluent, which is a 1:2 dilution. Let's say that I take 1 milliliter of this mixed up diluted specimen and I add 1 milliliter to this tube. Well, I now have 1 milliliter of my diluent in the new tube mixed with a 1/2 dilution from the original one. So this is a ratio of 1 to 1 diluent, 1 new diluent to 1 to 1. That's where people get confused, right? Because we're taking the ratio from the original and we're doing 1-to-1. This then is now a 1-to-2 dilution, or a 1-to-2 ratio, and not a 1-to-2. This is a 1-to-3 ratio. Pause for a second. Hold on. Sorry, we're good. Yeah, it would be a 1-to-3 ratio. And the reason why it's a 1-to-3 ratio, we have taken up in the original tube here, we have, don't do that, please. Stop hitting that button. We have a 1 milliliter specimen to 1 milliliter diluent. Over here, we have 1 milliliter of the previous tube to 1 milliliter of diluent. So it's 1-to-1 still, right? But we have to remember that this ratio now becomes the ratio for this bit. So this is now a 1-to-1 ratio there. But remember how parts are equal to volume, right? So this volume and this volume of this bit right here is not equal to the whole volume of what we've added to, right? Because if we've taken 1 milliliter out and our 1 milliliter is a 1-to-2 dilution, that means that of that 1 milliliter that we're transferring, half of it is sample and half of it is diluent. So that means that if you have 1 milliliter, half of 1 milliliter is going to be specimen and half of 1 milliliter is going to be diluent, right? So we now have 0.5 milliliters of patient to 0.5 milliliters of diluent. And then overall, we had originally added 1 milliliter of diluent. So this whole volume here is 1 milliliter of diluent. The value of a part in this tube is 0.5 milliliters, because that's how much of our breakdown we have. Versus over here, the value of a part is 1 milliliter. Okay, so because of that, you can divide 1 milliliter into 2 parts, because the value of a part here is 0.5, so you end up with 0.5, 0.5 of diluent. So you end up with 1 part patient, 3 parts of diluent. That's why it's a 1-to-3 dilution now, because you have 1 part here, 1 part here, 1 part here, 3. Cool? Which means that overall, it's a 1-4 dilution. This is why I don't like thinking in terms of parts, okay? This is why when we start getting into this, I like to think of it in terms of in terms of fractions, because it gets easier. Because we start to compare your tube dilution versus your overall specimen dilution. So, again, let's start with, just ignore this and pretend that this is my 100% pure sample, okay? No, actually, I want to keep it simple. So I put, let's say in this case, this is my tube 1, this is my tube 2, this is my tube 3, this is my tube 4, this is my tube 5, this is my tube 6, okay? I put 1 milliliter of diluent in here, 1 milliliter of diluent in here, 1 mil here, 1 mil here, 1 mil here, and 1 mil here, okay? This is my diluent. I put 1 mil of specimen into this tube. So then, specimen is going to be 1 mil, which means that my ratio of diluent to specimen is going to be a 1-to-1. And my dilution is going to be a 1-to-2, right? Because I have 2 total parts. Well, the math on this is where we get kind of funky. So we'll consider this, we'll talk about the difference between a tube dilution and our specimen dilution. Tube dilution is how much did you dilute from the previous tube to the current tube. So tube to tube is tube dilution. Tube compared to original is your specimen dilution, okay? So I have done a tube to tube, I've done a tube to tube, I've done a tube to tube, done a tube to tube, I've done tube to tube. Cool. So on this one, because this is my original, my specimen dilution remains 1 to 2. Cool? It's 1 to 2 because I have added diluent to it. If I have not added diluent to it, it is not a dilution. It's 1 to 1. So let's say that from my tube 1, I take out 1 milliliter of my diluted tube liquid, and I put it into tube number 2, and I mix it with the 1 milliliter of diluent already present. So I have added in 1 milliliter, which means that within my tube here, I have a 1-to-1 ratio of new tube to old tube, which means that my new tube to old tube ratio is 1 to 2. However, that's not what the value of my specimen is, because I have now diluted it by a factor of 2 twice. So in order to get my specimen dilution, in order to figure out what the concentration of the specimen is, I would multiply my tube dilution by my tube dilution. So my new specimen dilution is going to be 1 over 2 times 2, aka 1 over 4. Cool? All right, let's go into this. Let's say I take 1 milliliter out of tube 2 and put it in tube 3. So I've taken 1 milliliter. Again, my tube to tube, I've got 1-to-1 ratio of new tube to old tube, which means I have a 1 to 2 tube dilution ratio, or tube dilution factor. 1 to 2 tube dilution. In order to get the specimen dilution, I have to multiply 1 over 2 times 1 over 2 times 1 over 2. Because I have diluted by a factor of 2 3 times now. So this is going to be 1 over 2 times 2 times 2, which is going to equal 1 over 8. Cool? Another way of writing that would be 1 over 2 to the factor of 3. And all of a sudden we understand why we call it a factor, right? Because it's just an exponent. 1 over 2 to the third would be 1 over 8. Cool. I take 1 milliliter and I pop 1 milliliter in the next tube. 1 milliliter, I have a 1-to-1 ratio of new tube to old tube. 1-to-1 of new tube to old tube. I have a 1 to 2, again, dilution. I have now diluted by a factor of 1/2 4 times. So that is going to be the same thing as 1 over 2 factor 4, which equals 1 over 16. Are we starting to catch how it works? I take 1 and 1, I have 1 milliliter, I have a tube to tube of 1 to 1 because I have 1-to-1 ratio of new tube to old tube. I have again diluted by a factor of 1/2. I have now diluted by a factor of 2 5 times. 1 over 2 to the 5 equals 1 over 32. Last one, I take another milliliter. Again, new tube to old tube, 1 to 1. I have again diluted by a factor of 1/2 because it's 1 to a total volume of 2. But my specimen dilution is now diluted by 2 6 times. So 1 over 2 to the 6th, which equals 1 over 64. Math. There's a formula that we can use if you don't want to do all of this. So as long as you know that your tube dilution stays consistent all the way across the board, I have it written down because I didn't put it in the slides, you can do the dilution of your original specimen. So whatever the dilution is of the very first thing that you do right here. So this was a 1 over 2 dilution. So dilution of tube 1 times your consistent tube dilution factor. So for this, because everything else was diluted by a factor of 1/2, you would do it by, you would multiply it by, how do I want to say this? You would multiply by the dilution of the remaining tubes. So the remaining tubes are going to be a dilution of 1/2 in this case. And then you would multiply it by, why did I do that? Oh, that's bizarre. Okay. You would multiply it by total number of tubes minus 1. So in this instance, to get to tube 6, we would multiply by 1/2 times 1/2 over our total number of tubes is 6, and we would subtract 1 from that. So it would be the same thing as 1/2 times 1/2 to the 5th, which would be the same thing as 1/2 times 1/32, which is going to be the same thing as 1/2 times 32, which equals 1/64. That's how we would very quickly skip the whole line and get to tube number 6, okay? I just want to show one more application of how that math works. So let's say that our initial tube is diluted by a factor of 10, and then all of the remaining tubes are diluted by a factor of 2. And I want the dilution of tube number 4, okay? I would do the dilution 1/10, because that's my first tube, times the dilution of the remaining tubes, which is 1/2. And I would do the tube that I want, which is 4, minus 1, because I am trying to ignore this tube. So 1/10 times 1/2 to the 3rd, which should be the same thing as 1/10 times 1/8. So this specimen 4 would have a tube dilution, which is the comparison of the current tube to the previous tube, of 1/2, but a specimen dilution, which is the comparison of the tube's concentration to the concentration of the original sample, a specimen dilution of 1/80. Does that make sense? You survived. I know that the serial dilutions can trip us up. I will make a separate video specifically for serial dilutions, and or I will make a handout to explain what the heck is going on with serial dilution math. But just know that if you can remember that all that you have to do to calculate your tube is just first tube dilution times other dilutions to the tube that you're looking for minus 1, and this will give you your dilution, your specimen dilution, you are going to be okay. You will be okay. I am available for one-on-one tutoring sessions if you need more help with this math specifically, and we will drill down on this and we will get it done. We will figure it out. This is the one thing that I know that I can teach people how to do. I promise. I just need to be able to see you in order to effectively know that you're understanding it. So if you are not understanding this after this video, please let me know. I know that I said that this was going to be short, and I know that this ended up being an hour. I'm sorry. I'm so sorry. Anyways, thanks. I'm glad that these videos are helping some of you, and I'm sorry if this made it more confusing for others.